So hello, my name is Sandeep Mandal, and today we will be discussing about analysis of fan. Here we are discussing about axial fans, how to do a CFD analysis on that. We are discussing in stages. So our first stage of discussion is hand calculation. To design any fan, any axial fan, we have to do hand calculation first, depending upon our CFM requirement and where we are going to place this fan in actual condition. So there are different types of design calculation available, but in axial fan you have to refer some research paper and combine. In my case, I had referred different types of research paper uh, called from SAE or some other IJSERT and other publication, and I obtained some relation for that, and I calculated some uh, relative information, or depending upon our CFM requirement and air velocity requirement. The calculated parameters are air stream at outlet, torque, air horsepower, static pressure and total pressure obtained from axial fan, number of fan and caudal width of a blade. So these are the parameters are useful for calculating and for analyzing the axial fans. These parameters are also used as a input parameter in ANSYS or any FEA software. So depending upon this calculation, I have made some designs. So this is the basic design of axial fan I have made. It is totally as per my design, calculation and CFM requirement. So this is hub. These are the blades. Number of blades I have calculated, and this is the trailing edge of fan. This is the leading edge of fan. So in trailing edge, there are chances of most of the turbulence. So here you see the aerodynamic shape. To select this shape, you have to do a design calculation. Here my design calculation is specifying me as selection of subsonic aerodynamic structure. Also you have to calculate different parameters about designing a fan, that is blade caudal angle, this angle, slitting angle, and blade thickness, maximum thickness and minimum thickness. Here minimum thickness is 0 because it is a straight curve path following here, and I have done different iteration and designed different by changing the caudal angle and thickness and aerodynamic shape. I have designed different types of aerodynamic structure of fan so that our analysis should be perfect, and that this is the second type I had made. Here you can see the tilting angle from first region to second region. It is low pitch angle following towards outward radially. So by making this analysis, I have to suggest which fan is suitable, which fan is satisfying our requirement more precisely. There are some other, I have done 8 iterations, but I have shown you only 2. So these are the fan. Now for designing a fan, the noise is a very noise is very important characteristics to be considered. So noise is directly relating with the turbulence which a fan is creating while rotating in anti-clockwise direction when it is connected to a hub motor. So the turbulence is maximum created at the trailing edge. So I have made this very sharp so that the air which is flowing through aerodynamic shape is get evolved and get through this trailing edge and does not forming any turbulence here. Circular way eddy formation are less in this type of aerodynamic shape. In second model there is also eddy formation is less. So turbulence creation is a basic phenomena in fan. If we reduce the turbulence by changing our geometry, by changing our pitch angle or caudal angle, or by changing the caudal thickness of aerodynamic shape, so that is beneficial, but make sure that CFM requirement is constant. If you are changing this angle, the CFM you required is also changing comparatively. So here I am doing analysis in fluid flow fluent. First of all, we have to import a geometry in design modular. So I am importing a geometry. Make sure that your geometry is in step format. So the geometry is successfully uploaded. Here we have to create a enclosure first, in which we have to create a fluid domain where we have to include a fluid, and that is exposing our fan and vice versa. So cylinder. Here my axial axis is Z axis. Let it be. So here it is a fluid domain, but which section? Make it a uniform fluid domain in length. So this is our fluid domain. Now here two things. Here are two things. There are two main methods of analyzing this fan. That is, first we have to we have to create a boolean on this enclosure, and we have to subtract this geometry, blade geometry here, and then we have to fix this fan and rotate it at a desired RPM so that we get required CFM at the outlet side of this domain. Second method is fix this fan here and apply a inlet velocity or mass flow rate in kg per second or meter per second, where the air we can get simultaneously from rotating. We have to apply only that air in the terms of mass flow rate or meter per second from inlet domain, and it is coming out from outlet domain. So when the air velocity is coming from here, it is gets struck by this blade, and we get drag force, lift force, total pressure, static pressure, and turbulence level from trailing edge. So by analyzing this result for different geometry, we can conclude that which blade is giving better performance. So I have I created some results for this fan that I'll show you. So this is the result I obtained from analysis files. First of all, there is two things. During analysis, you have to select a laminar flow and K epsilon value for and standard initialization process in the analysis fluid domain. When you do analysis in this format, in setup file, you have to select laminar flow in CFD post and K epsilon value. And if your laptop is of low RAM, approximate 4 GB or 8 GB, the set up a iteration value up to 20, because it take 7 to 8 hours to calculate this kind of stuff. If you take iteration up to 100, you have to take very large computational time. That's why I'm not showing you the calculation procedure. I'm showing you direct result. This is the static pressure I obtained. See, from here our inlet domain is on the back side and outlet domain is in the front side. The air coming at 33 meter per second, which I have calculated in my hand calculation. This is the blade and this is trailing edge. So you can see that the trailing edge having less pressure, approximate 3.54 e raised to +2, because this blockage of this blade, when the air is entering from inlet domain, the blockage is provided by this trailing edge, but the more blockage is provided by trailing edge because it is in outward radially with the pitch angle of 40 degree. This is the total pressure which I have obtained. It is maximum. It is giving you maximum and minimum value. It is a surface solid zone which I have selected. You can see the air velocity is diverting with the blade. The same phenomena we are getting if we rotating this blade at particular RPM for the generated CFM. At that time, the red portion is in backside and this bluish and greenish and yellow portion is backside. So this is the total pressure. Now the axial velocity. We can see that overall fluid domain is filled with the air and axial velocity is maximum up to 106.0485 meter per second. What does this mean? We have given a air velocity is 33 meter per second. When it is obstructed by blade at 40 degree pitch angle, the velocity of air will be increasing. So vice versa, when we are rotating a fan in actual phenomena, we are getting a outside or outlet velocity is 106.0485 meter per second. Here the radial velocity is 66.043. It is a outraged velocity which is diverging at the hub. Turbulent kinetic energy. So this is showing turbulent energy in meter square per second square. The lower the value of this turbulence, depending upon the other iteration, we can select the noise level. Lower the value of turbulence kinetic energy, lower the noise level of fan. Turbulence intensity, it is showing 40%. Turbulent dissipation rate, here it is considering epsilon value so that the analysis will be diverging from the kinetic turbulent energy. Okay, this is turbulent kinetic energy of fan domain. Here only fan is showing that the air molecules are flowing through the fan and lower portion of air will be struck by leading and trailing edge. Similarly here the mass flow rate we have calculated is 43 in ideal calculation, but the fan in analysis we have obtained is 52. This variation is considerable here because 10 kg per second is considerable here because it is calculating all the calculated within all fluid domain and we are calculating only in z direction. This is static pressure value. This is total pressure, turbulent dissipation rate, turbulence intensity. It is coming out to 40%. You can see here the blade domain is highlighted here. So you can see here I have iterated all, I have analyzed all the geometry I have created, and depending upon that I have created one Excel sheet so that comparison for the bleed analysis should be easy for me. So this is static pressure, total pressure, axial velocity, turbulence intensity, drag and lift force on the fan, and mass flow rate. So you can see it is approximately same on 3. It is 40-degree pitch angle, 35-degree pitch angle, and 30-degree pitch angle. As you goes on decreasing the pitch angle, here you see a turbulent intensity percentage is increasing and turbulence also increasing. So our conclusion is that the turbulence, we have to create a lower turbulence. So 40-degree pitch angle is optimum ratio for that, so that our noise level should be reduced for 40-degree turbulence angle. But for different types of fan, the fan we are using on drones, that will produce a bigger effect. So there are different other fans also. So in this way you can design a fan, and by calculating different parameters for different fans, you can evaluate or compare results for different fan. And note the one thing, you have to reduce the turbulence level very precisely. If you reduce the pitch angle, there should be a deductment in CFM requirement. Or if you increase the pitch angle, there will be or if you increase a pitch angle, then there will be an increment in noise after 40. I'm saying after 40. So that's all about fan analysis.